previously we had an introduction to vector functions. Now we're going to do calculus with vector functions. So that means two things. We're going to do talk about derivatives and integrals. Also talk about some applications. So first, let's take a look at the derivative for vector functions. I'm happy to say the derivative of a vector function is exactly what you think it is. You take the derivative of each component. And the variable is going to be the parameter, which is what we would expect. So let's take a look at a problem. So suppose you got the vector function r equals 3 minus t, comma, t squared, comma, cos t. So let's find the derivative dr dt. Well, dr dt is just take the derivative in each component. So you get negative 1, comma, 2t, comma, negative sine t. Okay, so this is pretty straightforward. All right, so a little bit about notation. So the notation, some of the notations are pretty much exactly what you would expect. We will, for the most part, stick to the first notation, writing dr dt. So what about some applications? So the most typical way to understand a vector function and its derivative is to say that the vector function represents movement. So the vector function represents a position, and then its derivative, which is dr dt, that would represent the velocity. So it'd be a velocity vector, which we could write as dr dt. We could also just write it as v. That's pretty standard. And the derivative of velocity is acceleration. And we could write that using our second derivative notation, second derivative d squared r dt squared, or as the acceleration vector, we just write it as the a vector. Now, what about speed? Well, speed, as you might remember, is the magnitude of the velocity. So here we have a couple different notations for that. So now that we've set down this application context, let's do a problem with some calculations. So for the position vector r of t equals 2t minus 1, comma, e to the 3t, comma, 4t minus t to the 4th. Let's find the velocity and acceleration vectors as well as their magnitude. So let's do it. So the velocity vector that equals, taking derivative one component at a time, 2, and then 3 e to the 3t, and then 4 minus 4t. And now we can find the speed, which is the magnitude of that. Magnitude of the velocity vector is just, well, it'll be 2 squared plus 3e to the 3t squared plus 4 minus 4t squared squared, and then square root of all that. And we could multiply it out or try to simplify, but I'll just leave it as is. That's all we need. So next, acceleration. So the acceleration, another way to think of this is just the derivative of the velocity. And that is, again, going component by component to take the derivative. 0, 9 e to the 3t, and then negative 12 t squared. And now the magnitude of the acceleration is just, we'll have 0 squared. I didn't need to write it down, but I did just for completeness. Plus 9 e to the 3t, all that squared, plus negative 12t squared, square that, and then take the square root of the whole thing. And there's the calculation. Now, curiously, for the magnitude of the velocity, there's a word, speed. Magnitude of acceleration does not have its own word. You just have to say magnitude of the acceleration. Okay, so there's one application of derivatives for vector functions. Another application. Let's talk about the tangent line. So we've previously seen is that in calculus in 2 dimensions, the direction of the derivative is tangent to the curve. This continues to be true in 3 dimensions. In fact, it's true to any number of dimensions. So at a given point on the curve, the velocity vector is tangent to the curve. And just to remember this, whenever we calculate a tangent vector, we're calculating it at a specific point. So when we draw that vector should start at that given point. Don't start it at the origin. So this tangent vector we could also think of as the direction vector for the tangent line. Let's do this in a problem. First, we'll do one in 2 dimensions. So for vector xy equals 3t comma t squared, first we're going to draw the curve and a tangent vector at t equals 2. Then we're going to find the equation of the tangent line at t equals 2. So drawing this curve actually had the computer software do it for me, along with the tangent vector at t equals 2. So of course you'll notice at t equals 2 we have to figure out where we are on the curve. So I'm actually going to write down that calculation. So what point is that? So the point when t equals 2, you'll have 3t, so 3 times 2 comma 2 squared, and that point is just 6 comma 4. And that's the point that's marked on the graph. Then what about the direction vector? So the direction vector v is just dr dt. So taking the derivative, you get 3 2t. Now, of course, we want that at the value t equals 2. So dr dt at t equals 2. So that's going to equal, plugging in, we just get 3, 4. So putting that all together, we can write down the equation of the tangent line. We like to call L. So the equation for the tangent line L, written in vector form, we know we can just write it as the original point, which was 6, 4, plus our direction vector 3, 4 times a parameter, and we like to use t. So to bring things full, so that's how you do this calculation to find the equation of the tangent line, and here it's written in vector form. Now to bring this full circle, let's do the problem using y equals f of x. So first of all, we're going to rewrite the original function in terms of y equals f of x. So note that originally we had x equals 3t, which tells me that t equals x over 3. And since y equals t squared, that tells me that y equals x over 3 squared, which is just 1/9 x squared. So finally I've got this in y equals f of x form. Now let's go ahead and find the equation of tangent line. So what's a point? Well, when t equals 2, since x equals 3t, x equals 3 times 2, which is 6. And then y, of course, equals t squared, and that's just 4. And now let's find the slope. The slope is dy dx, which was just, so derivative of 1/9 x squared, so 2/9 x. And now we want that at our point, which is where x equals 6, and that equals 2/9 of 6, which when you simplify is just 4/3. So this method, using y equals f of x, we get that the tangent line is y minus 4 equals the slope 4/3 x minus 3. And so again, from our work on lines, we know that these two equations are the same. On the left, oops, sorry, I wrote down the wrong point. Looking at the wrong thing. Y minus 4 equals x minus 6. There we go. Wrong x value. So there we go. So once again, looking at these lines, we know that they are equivalent. They describe the same thing. So we know that we have the original point. On the left side, you see the point 6, 4, and on the right side, you can plot the point x equals 6, y equals 4. That's the known point. And then further, the direction vector of 3, 4 gives us a slope of 4/3, which is the slope in the other equation on the right side. So these are equivalent, which is what we expect. That's how it should be. That's how it looks doing the problem in 2 dimensions. Now, what about in 3 dimensions? So in 3 dimensions, it's much easier to work just with vectors, and that's what we're going to do. So for our vector function, xyz equals cos t, sine t, t, something that we've seen before, first we're going to draw the curve and a tangent vector at t equals pi/2, and then we're going to find the equation of the tangent line at t equals pi/2. So, of course, all this is in 3 dimensions. So for drawing these things, we're going to use software, and that's what I've done. So here is that graph. So again, we know that this is the equation for a helix. And there's the graph. And then the tangent vector at t equals pi/2, just drawn in what looks like a straight line tangent to that point. Now we're going to get into our calculations. So once again, to write the equation of the line in vector form, we need a point and direction vector. So let's get it. So first at the point. So the point, we need our function at pi/2. So that gives us cosine pi/2, sine pi/2, pi/2. And that just equals 0, 1, pi/2. So there's our point. Next, we're going to get direction vector. So our direction vector, which we like to call v, equals, we know that just comes from the derivative of the vector function. So dr dt equals negative sine t cos t 1. And of course we want this specifically at our t value. So the direction vector at pi/2 equals, just plugging in and evaluating, negative sine of pi/2 is just -1. Cosine of pi over 2 is just 0. And then 1 is just 1. So put that all together and we can get the equation for the tangent line. xyz equals, take our given point, 0, 1, pi over 2, plus direction vector, -1, 0, 1, times our parameter, and we like to use t. And we can do something interesting with this. So first I should say, so that is the calculation in order to find the equation of the tangent line using derivatives. So just as a fun little exploration, we can see what this looks like more dynamically. Not just the tangent vector at a single point, but the tangent vector at any point. Let's take a look. So here, again, using this software, I'm using Mathematica. I have a sketch of the function, which is the helix, and I've also drawn in the tangent line. So right now we're at the t value, so the value for the angle is 0. So you can see where that point is on the graph, and then I've just got in red a little tangent vector coming out there. We can see what happens as we go around the graph. So, and again, this is happening in 3 dimensions, but we're looking at it in a 2-dimensional image, 2-dimensional screen. So you have to imagine what's going on here. So we've got, at this point, so now I'm at an angle of 1.78 radians, and that marks that point. And again, you can see we've still got a tangent vector. And we can just trace this to any point on the graph. Here the tangent vector is almost pointing directly at us. Then we swoop around and we're, again, tangent vector, tangent vector. So anywhere we go, so you could think of this as a direction, so v is like a direction vector function. Tell me the point, tell me the t value where we are, and I'll tell you what the direction vector is. Let's talk a moment about the formal properties of derivatives on vector functions. Because it's basically you're going component by component, the properties are very familiar from just derivatives for regular functions. So we've got the derivative of the sum of the vector functions is the sum of their derivatives. And notice that on the left side, I've written this out in full notation, and on the right side, it's in a very brief notation, which might be helpful when we're trying to write a lot of stuff down very quickly. So then we've got derivative if there's a derivative rule for if there's a scalar multiple. Then we've got a product rule. Then we've got, so those 3 are pretty much what you'd expect. Now, the last 3 are sort of more interesting. They're a little newer because, so the 4th rule is a rule for the derivative of dot product. And amazingly, you basically wind up with a product rule. So the derivative of u dot v is the derivative of u dot v plus u dot the derivative of v. And then we also have a similar rule for the cross product. And amazingly, you also wind up with a cross product, with a product rule when taking the cross product of 2 vector functions. And then finally, we also have a chain rule. So if you have a vector function of some function of t, you basically just wind up with a chain rule. So the derivative of u, where you're plugging in some function p of t, is just du dp times dp dt. Okay. So next, we are going to prove a little fact that we are going to need later. So prove that if a vector r, so a position vector, has constant magnitude, then it is perpendicular to its derivative, which again we can think of it as the velocity vector. So the first step is to write down what does it mean for a position vector to have constant magnitude. But it's easy. We just write down its magnitude as c. We assume c is some constant. Okay. Now the next step is really slick. We're going to try to rewrite this in terms of vectors, but without the absolute value bars, because absolute magnitude bars are tricky to work with when we do calculations. So we square both sides. Now, why do we square both sides? Because we know that the magnitude of a vector squared can be rewritten using dot product. So now we have that r dot r is c squared. And now we do the key step. We know we want to eventually make a statement involving the derivative of r. So now we take the derivative of both sides and we see what happens. So the derivative on the right side, it's just a constant. So the derivative on the right side will be 0. What about on the left side? On the left side, we have to use the rule for the derivative of a dot product, which we just indicated. So on the left side, using prime notation for derivatives, we get r dot r prime plus r prime dot r. Now we also know, just from our rules of functions and dot products, that dot product is commutative. So those are actually both the same thing. So that actually says that 2 r dot r prime equals 0. Well, that immediately tells us that r dot r prime is 0, and we know from our rules of vectors and dot products that when the dot product of two vectors is 0, they are perpendicular. Therefore, r and r prime are perpendicular. And so we've proven our little fact. So this was a look at vector functions, which we can now talk about in 2 dimensions or 3 dimensions or any number of dimensions. And we did some calculations, some applications, and we also proved this little fact, which we're going to use later.